So we are on part 5 of using trig identities to verify equations. So we are still going to be using the reciprocal identities and the quotient and Pythagorean identities. Tomorrow we're going to introduce 2 more identities or things that we're going to be using. So these are some quick guidelines that I kind of have said over and over, but just in case you want to go over them one more time, there they are. These are all examples that you could either factor or perfect square trinomials or that you would see. So this is something you probably would see in Math 2 or Math 3. Since they're both the power of 4, they're basically, you can separate them into 2 binomials, your positive and your negative. So think of it like your difference of 2 squares, because technically anything that's even, you can separate as a power of 2 squares. And then since this is still negative right here, that could still, it's still a difference of 2 squares, so you could break it down again. And then again, this is a different 2 squares, so you could break that down again to that. So it's just breaking it down again and using your properties from Math 2 and Math 3 that we learned. And you're using that same thing with trig functions. So again, this is the difference of 2 perfect squares, because you have perfect squares, and 4 and 9 are perfect squares. So you could write them as 2 different binomials. Since cosine of x and sine of x are not perfect squares anymore, or have the even power, this is what the answer would be for that one. So I need to change this piece right here to look like this piece. I want you to notice that on both sides, I have a 4. Sorry, I thought it was my highlighter. I have a 4 on both sides. I have the negative. What I need is a tangent. So we know that tangent of x squared plus 1 is equal to secant squared of x. So if let's just say, factor out a negative from both of these, I'm going to get a positive secant of x minus 1. Okay, and now that I have that, I'm going to say, okay, well, now I can manipulate this and say, okay, well, if I move now the secant and I subtract the 1 from both sides, I'm going to get what I have. This is not the only way to see it, but I think this is the fastest way to see it. And now that I know that, I could actually replace this tangent right here with this secant of x minus 1. So now I'm going to have 4 minus the tangent squared of x. And now I have verified that the left side equals the right side. Well, on this one, I need to verify that all of this equals to 1. Well, one of the first things I want to notice is I need to get rid of everything, and it has to turn into a 1. And the thing that I'm going to do is I'm going to notice that they're conjugates of each other. If you remember what conjugates are, it's basically the same thing. They just have an opposite sign. And when we have conjugates of each other, the 2 middle terms cancel out. So all you technically have to do is your first times your first and your last times your last, because your 2 middle terms are going to cross out and go away. If you don't believe me, you can work it out. Secant of x and secant of x, that's secant squared of theta. Tangent times negative, that'd be negative tangent squared theta. Okay, and we know that secant is equal to this, so we could substitute it. So we could have 1 plus tangent squared of theta minus tangent squared of theta, and then we're going to get that these 2 go away and we get 1. This is not the only way to do it, but this is one way to actually do it and verify. I actually think this is probably the fastest way to verify it, but there's other ways. Again, we have to try to remember our stuff from Math 2. We know that this exponent right here means we have 2 copies of the same thing. So we are going to have 2 binomials of cotangent x minus 1, and we're going to FOIL them out. So we're going to get this times this is going to be cotangent squared of x. This one times that one is going to be negative cotangent of x. Then we're going to have negative 1 times that, again a negative cotangent of x, and a negative times a negative 1 is a positive 1. Then you're just going to combine your like terms, and we should have cotangent squared of x minus 2 cotangent of x plus 1. Okay, so now if you notice, we have this piece that we wanted. So somehow the cotangent squared of x plus the 1, we have to try to get rid of it. So I'm going to rearrange it, and I'm going to put the negative cotangent in the back. So I have now cotangent squared of x plus 1 minus the 2 cotangent of x. And if you notice, this piece right here is one of our Pythagorean identities that we could use. So hopefully you know, that cotangent squared of x plus 1 is equal to cosecant squared of x. So this right here becomes cosecant squared of x minus 2 cotangent of x. And that's literally what we needed. We verified. I believe that on your sheet, it's the one, then this. Remember, addition is commutative, so that's okay. So I'm hoping that you guys see this and see this is the difference of two squares. One, it's a perfect square because 1 times 1 is 1, so it's there. So, and you know, 4 is an even exponent, so that's anything that's even, it's you could break it down into perfect squares or binomials. So what I'm going to do is I'm going to break this down into binomials. I'm using my math 2 and math 3 information or knowledge. Now we're going to have secant squared of x minus 1, and then we're going to have of x plus 1. From there, we know that this piece right here is a Pythagorean identity. That becomes tangent squared of x times secant squared of x plus 1. Okay. And if you notice, my final answers are in terms of sine and cosine. So this is probably where it would be the best place to start changing things to sine and cosine. So I'm going to change the tangent squared to sine squared of x over cosine squared of x. And I'm going to change the secant to be 1 over cosine squared of x plus 1. And now that we have that, we can get a common denominator for this part. Oops, I thought that was my highlighter. This part right here. So I'm going to have, let's see, sine squared of x over cosine squared of x. And if I put all of that over cosine squared, I'm going to have 1 plus cosine squared of x. Once we have that, all we have to do is multiply the numerator times the numerator, denominator times denominator, and hopefully this will give us what we need. So if I go sine times everything that's in the denominator, I'm going to get sine squared of x plus sine squared of x cosine squared of x, and which is what we have in the denominator. And then we have cosine squared times cosine squared. That'll be cosine 4 to the 4th power x. And that is what we have. So we have verified it. Last one. I suggest that you try this one by yourself. So pause it and then check your answer with mine. So if you notice, these are conjugates of each other. So again, if you remember what conjugates are, you could work less. So you go just first times the first, last times the last, because the two middle terms of conjugates always cancel out. So we're going to have 1 times 1 is 1. Cosine times that is negative cosine squared of x. And we know that this right here is a Pythagorean identity, and that equals to sine squared of x. So that is our verification that the left side equals the right side.